In this video, we're going to take a look at the intermolecular forces that form in nonpolar molecules using the molecule CH4 as an example. So just to demonstrate why CH4 is a nonpolar molecule, if we compare the electronegativity values of hydrogen and carbon, 2.6 and 2.2, which means that the difference in electronegativity is only 0.4, which is quite small, and therefore the electron movement from hydrogen to carbon is not particularly significant. Now, we can't really compare lone pair symmetry because neither carbon nor hydrogen have lone pair electrons. And if we look at the way that electrons move by drawing all of the dipole vectors here. So if we look at the left side of the molecule, we see these two hydrogens, their electrons are going to be moving towards carbon like this, and these two hydrogens here, their electrons are also going to be moving towards carbon like this. And while it's difficult to gauge this because we can't look at this molecule in 3D, if we look at the overall movement of electrons, it looks like the electrons from these hydrogens and the electrons from these hydrogens are moving with the same magnitude. 0.4 is the electronegativity difference on both sides, but moving in opposite directions. Now, if you have electron movement that goes in opposite directions with the same magnitude, the two cancel each other out. What this means is that there is no side of this molecule that is positive or negatively charged the way that we see with polar molecules like water. That means we need to analyze the charge or the polarity of these molecules a little bit differently. You'll notice that I've drawn two CH4 molecules here, but that I have not drawn in any of the bonds because we know that one bond is two electrons. Now, there are a few questions that we can ask about electrons here. Number one, can you see electrons? Obviously no. Number two, do electrons ever stop moving? Again, the answer is no. Number three, because electrons are so small that we will never be able to see them, and because they never stop moving, is it possible to know where any electron is at any given time? Well, again, the answer is no. Now, remember that one bond is two electrons, which means that among just the bonds of the carbon and the four hydrogens here, that means we have 8 electrons. So that can mean that 1, 2, 3, 4, 5, 6, 7, 8. That can mean that for at least a split second, all 8 electrons in all of these bonds can all be located here because, again, electrons never stop moving and it's impossible to know where electrons can be. Now, are the electrons going to stay in this bottom corner of the molecule? No, obviously not, because electrons have the same charge, which means they're going to repel each other and scatter in different directions. However, if we stop time and if we split this molecule in half like this, because all 8 of the electrons in the 4 bonds are here, that means that right now, the left side of this molecule has more negative charge because all the electrons have moved to this side. Conversely, the right side of this molecule has no electrons, which means right now, the right side of this molecule has a temporary positive pole. And again, are the poles in this structure permanent? Well, that answer is no, because electrons never stop moving, which means they will move from this spot, and electrons are repelling each other, meaning that the negative charge of each electron are going to push each other away. However, right now, if we assume that these charges here, or these partial charges here, are in this molecule on the left, where in the molecule on the right will its electrons want to go? Well, we know that negative charge does not want to stay together. It wants to go towards positive charge. which means the 8 electrons in the bond over here, 1, 2, 3, 4, 5, 6, 7, 8, will want to be on this side of the molecule so that this negative charge from the electrons all on one side can attract to this positive charge here, because again, electrons don't want to stay together. They want to attract to the opposite charge, which would be here, because all the electrons in this molecule are on this side here. This attraction that we have just shown is what is called a dispersion force. Sometimes in chemistry, we refer to this as a London force in reference to the school of chemistry that originally discovered this force, but the word dispersion force more accurately describes what's going on here. We know that the verb form of the word dispersion is the verb to disperse, and another word for the word to disperse is the verb to scatter. Again, we don't know where electrons are. Electrons never stop moving, and it is not possible to predict where they are going to be. In other words, the electrons are dispersed randomly across the molecule. And when they happen to disperse into highly concentrated areas such that one side of the molecule temporarily has a negative side and attracts to the side of the another molecule with no electrons with a positive side, this causes a dispersion force to occur. But as we've already established, these are not permanent, because when the electrons move away, this negative charge is not in the same place anymore. And if the electrons move to this side, then this positive charge is gone. So these poles that we've drawn here are not permanent, which means that the dispersion force, the attraction between these poles, is not permanent either. And for that reason, dispersion forces are considered the weakest of all intermolecular forces, because they are by their very nature temporary. That being said, are all dispersion forces equally strong? Well, if we consider CH4, which only has the 4 bonds, that means it has 8 electrons from the 4 bonds. If we compare it to CF4, well, what does fluorine have that hydrogen doesn't? Fluorine, as we remember, has 3 lone pairs, and when it's in this molecule, is going to have the bond as well. That means that each fluorine has 2, 4, 6, 8 electrons, and 8 times 4 is 32 electrons. Now, again, let's, for the sake of argument, position all 8 of the electrons on one side of this molecule. 1, 2, 3, 4, 5, 6, 7, 8. Now, at this point, again, these 8 electrons are not going to stay here forever, but while they are here, this side of the molecule has a negative charge, and this side of the molecule has the positively charged pole. Now, let's do the same thing with CF4, but now instead of putting 8 electrons, we're going to put all 32 electrons in the same area here. Again, are they going to stay here? No, because they're going to constantly disperse randomly throughout the molecule, and they will be repelling each other because of their negative charge. But while they are here, does this molecule have a weaker or stronger negative charge than CH4? Well, if it has more electrons, that must mean that it must have more negative charge, because you have more electrons with negative charge in the same place. That means because the right side of this molecule has lost more electrons to the other side, the positive charge is also going to be stronger. But once again, are these electrons going to stay on the same side of the molecule forever? Again, the answer is no, because they disperse throughout the molecule. So because fluorine has lone pairs, that means that tetrafluoromethane, CF4, has many more electrons than CH4 does, And as a compound's number of electrons increases, that means that the negative charge and the positive charge that result from a temporary dispersion dipole also is going to get stronger. And if the dipole gets stronger, that means the attractive force that it forms between other molecules with dispersion dipoles is also going to be stronger than before. In the next series of videos, we're going to look at how molecules behave once they are put into a solvent and how polarity, both in terms of hydrogen bonding and nonpolar attractions such as dispersion forces, can be used to predict what compounds will dissolve in water and what compounds will not.